All right, we're in this video going to look at limits again, but this time we're doing them algebraically. So you can always use graphs if they're available, but if not, we want to learn how to do these algebraically. So the first step in doing these is there's three options, right? Step one, direct substitution. If I have a function and we want to know the limit as x approaches, say, 3, the first thing we want to do is plug in 3 and see what happens. If we get a number, then that number is our limit and we're done. So let's try that. Example 1, 2x squared minus x plus 1. We're going to plug that thing in. We're going to say not responding. There we go. 2 times 3 squared minus 3. So we find that the limit as x approaches 3 is 18 minus 2, 16. We got a number. Looks pretty good. We could graph that if we want, but we don't have to because we know that if we plug it in and we get a number, that's our answer. So, example 1, done. Boom, let's move on. Okay, this one here, we're going to try the same thing, and we're going to say 1 minus 1 over 1 squared minus 1. That is 0 over 0. That isn't going to work. So, step 2, if we have to do this, if step 1 didn't work, and we get a 0 in the denominator, then we go on to step 2. And step 2 is this. We're going to, for my own sake, saving some room, we're going to try and factor it. So x minus 1 on top, can't really do anything with that. But the other one, we can say x plus 1, x minus 1. That's factoring that because that is a difference of squares. So the goal is we factor it and see if we can't do this. Hey, look, we have a factor in the top that cancels a factor in the bottom. And then let's try and plug in 1. So now what this looked like was 1 over x plus 1. So we get 1 over 1 plus 1. So our limit as x approaches 1 equals 1 over 2. Okay, so it worked. Thank goodness. Step 1 didn't work. Step 2 was to rearrange it, factor it, do something with it, see if you can't get those like terms to cancel top and bottom. And we did. By doing that, we find that we have a hole at x equals 1. But just because we have a hole doesn't mean that we don't have a limit. In fact, a hole means that we were going to be continuous. It's called a removable discontinuity. Next up, let's take a look at this one. So this one here, we're going to plug in 0. So 0 plus sine of 0 is 0. Because remember, we need to keep all those trig values in our heads for next year. 0 plus 0 over 0, that's not good. We need to do something. Well, we really can't do a whole lot of rearranging. We could say x over x plus sine x over x. Like we can split the bottom, or split the top with the same bottom, but we still have a sine x over x. No matter what we do, this is not going to work. So what we have to do instead is we need to graph this. There's no way around it. Now, again, what I said in class when we did this is algebraically, in order to do this without a graph, you need calculus tools. You need to know how to find the derivative of this function. And the derivative ends up being 1 plus cosine of x. Okay? And what we find is if we were to plug in 0 for x, that's 1 plus cosine of 0, which equals 1 plus 1, which equals 2. So let's check that. I'm going to box it in. I'm pretty confident. But let's try this. X plus sine x over x. I don't need that. I want decimals. There we go. Y equals x plus sine x over x. Okay, there it is. Again, graphically, as x is approaching 0, hey, look at that. Oh, we do have a hole right here, right? Because we have a term that canceled with the bottom. But from left and right, we're approaching 2. So graphically, because you guys would have had no idea how to find that derivative I showed you, but graphically you can say, the limit is 2. Okay, moving on, one more. Plug this in. We have an x with every term of each binomial. If you plug in a 0, everything becomes 0. So what I want to try and do is factor out x squared. So we get 6x minus 2. And we factor it out. We factor it out there. We factor it out again on the bottom. X squared plus 1. Now, if we try, well, first of all, those reduce. So I'm going to plug that in. I'm going to say 6x minus 2, where x is 0. So I see a negative 2. And then here we get 0 squared plus 1. So we get 1. So the limit, as it approaches 0, is negative 2. So this here was direct substitution did not work. Step 2, we tried to rearrange, factor, whatnot, and factoring worked. So we did not have to go to graphing. But anyways, there you go. Let's see how much time we got left on this. Looks like, yeah, let's go ahead and do these. Let's talk limits at infinity. Shouldn't take too long. Sorry. Infinity. That's the idea that on our graph there is infinity way down here. As x is approaching infinity, as our graph is doing whatever it's going to do, we want to know what is this tendency? What is it going to head towards with really big numbers? So when we do that, we have, like I've said before, we have 3 different possibilities. We're looking at what is called the law of dominance. The law of dominance says that as our x gets really, really big, like to infinity, all the smaller terms become irrelevant, basically. So let me draw an example here. So if we have, say, for example, geez, I don't know, 3x cubed. As x gets really, really big, the minus 5 at the end isn't going to affect the graph a whole lot. Same thing. We get x really big and we take and cube that, then the x itself isn't going to be as significant. Neither is the x squared. So the law of dominance was the idea that as we go to infinity, the negative 5, the x, the 2x squared, really become negligible. And so what we're left with is just simply looking at, for the limit, we're just trying to focus on that largest exponential term. So in this case, we will look at this graph and say, what is x cubed going to do? Well, it's going to get really, really big and go on forever. In this case of our first example here, we have a fraction. So what we're really trying to do is look at both the top and the bottom, and we have 3 options. We're going to have like an x to the 5th over x squared. We're going to have an x cubed, let's go 2x cubed over 1x cubed. Or we're going to have x cubed over x to the 4th. So of these 3 options, we are either going to, as x gets really, really, really big, the top is going to get really big faster than the bottom. So we're going to have big over small, which just reduces itself to big. So this means that the limit, as it goes to infinity, does not exist. The limit doesn't exist because as x is getting bigger, raised to the 5th power on top, it's outperforming the x squared on the bottom. So you have a really big number over a small number, which is just a really big number, or infinity. So we say the limit doesn't exist. I'm going to jump to the third one here quick. The third one, we have x getting really, really big, well, on the bottom, it's getting bigger faster than it is on the top. So this one is becoming, again, this is a very gross generalization, but as the video is going here, I'm wanting to emphasize just the generalizations. So small over big will eventually tend to 0. Okay, again, very big generalizations, but just like our first one, as x is getting really, really big, the bottom will get bigger faster, so we get small over big. Well, think of that as like 1 over a really big number is tending towards 0. So this one, the limit is 0. Now, with all of that in mind, I'm going to kind of reduce some of this, so it's not as messy. Let's focus on the middle one. If the rate at which my top and bottom get bigger is the same, so if they get bigger on the top and the bottom at the same rate, what we find is that the ratio of the coefficient of that big term, so -7 and 1, is the limit of our function. So in this case, it would be 2 over 1, or just 2. Up here in the example problem, we have -7 over 1, which is just -7. And there you have it. That's how you evaluate limits to infinity. You have 3 cases. You either have a higher exponent on top, and you go to dne because you're going to infinity. You have a higher exponent on the bottom than you do on top. If that's the case, your limit is 0. And if the exponent, the leading exponent, is equal top and bottom, your limit is just simply the ratio of the coefficients of that term. And that's where we're going to end this video. I'll pick up the next one and finish out the lesson.